have 5 talks this afternoon, and the first one will be by Dimitris Saraidaris, who's going to tell us about searching for emergent space-time in spin glass.
Yeah, hello, I'm Dimitris. First of all, thanks all the organizers for giving me the opportunity to give a talk in this annual workshop. It's always a pleasure to be here. I would like to talk about a project that we finished very recently with my friend and collaborator Lev Saposnik. We're both based at the Freie Universität in Berlin, and we're both PhD students. So this project kind of combines two different ideas that exist already in literature, and they're a bit far away from each other. So I've decided to spend most of the time discussing about these two ideas, and in the end I will show some results and how we try to combine them. So I will go 5 steps back, and I will ask what is a duality. And a very simple way to think about it is to assume that we have two distinct systems that we can describe with two different Hamiltonians, H1 and H2. And if we can find some relation between their observable states and dynamics, then we could call the relation as a duality. So a very simple example is the Ising model is a chain of spins, and we can find a non-local transformation, in this case the Jordan-Wigner transformation, and write down the Hamiltonian, the H1 as the H2 you see on your right, which is like now a Hamiltonian with different degrees of freedom with Majorana fermions. However, there is the map between the Hilbert spaces of these two different systems is an isometric map. And also we have a linear map between the two Hamiltonians. These two Hamiltonians describe exactly the same physics. Transformation didn't change anything. So we can say that these two systems are kind of dual with this very general definition we gave. So now we do the next step, what is holographic duality. And now we can think of it as the duality the way we described it before, but now between two systems or two theories of different dimensions, from d dimensions to d+1 dimensions. And we can make our lives very easy if we just think of a theory in 3 dimensions and choose the cylindrical coordinates and think of that theory living in the bulk of this cylinder. It can be described by an action, let's say, and then if there is such a duality, there should be a theory or a system on the boundary, living on the boundary, which we can describe with a different action, the boundary action. Let's say that the theory in the bulk is described by some operators phi, the theory on the boundary by some operators O. Then if there is such a duality, we should be able to find a connection between the operators of the one theory with the other. So there should be some kind of an expression like this, which is connecting the O with the phi operators, where kappa or k is a smearing function or it's a propagator from bulk to boundary. So from now on, whenever I say the bulk emerges or emergent bulk from a boundary theory, I will mean it's the same as saying my boundary theory is holographic or my boundary theory has a dual.
So, sorry to interrupt you.
Sure.
So here your lambda O is in 1/n. So it is the case in some instance of ADSLT, but is it always the case when you have this kind of duality between d-dimensional system and d+1 dimensional system?
This is very general. I didn't mention ADS or CFT. Yeah, if you want a gravitational theory on your bulk, you should find a connection, a relation between the operators from the bulk to the boundary.
Yes, exactly, but I am asking about what you neglect, your O of 1/n. So what is this n in general?
What's the definition of n? Are the degrees of freedom of my theory.
It's always like that.
No,
This setup
you're right.
I'm sorry?
Well, it is generic.
Yeah, that's
Is it just you neglect something and you write it?
yeah, I'm just writing all the terms that go as 1 over n. I'm not saying something important here, I'm just saying that there should be a connection, because in the end, later I will take the large n limit, but generally I should find such a relation if I want to claim some duality between two theories. There is no gravity yet.
Okay, but just to mention that you could find dualities which are holding in the same regime, for instance, not weak strong or in
Okay.
the Largian regime, etc. So I was just questioning about the generality of this kind.
Yeah, thanks.
But so can I interrupt?
Sure.
But here we're also making some assumptions about the field theory side, right? I mean that, like, for example, there is a mass gap. And
Yeah. Okay, yeah, sure. But that was a slide just to go naturally to the next, to the first idea that pretty much inspired us, and it's based on the paper you can see below. And now let's assume that we have a large n system living on the boundary, and we want to find conditions, if there are, for the bulk to emerge. And as I said, whenever I say bulk emerges, I mean my boundary theory to be holographic. So let's assume we have a boundary. I'm making stuff even more simpler. We have a boundary, this red line, and let us assume that there are some operators living on this boundary region between minus t to t. These operators I call O of t. Then, based on this paper here, we can find some smearing functions f of t, and we can define some new operators, smeared operators O of f, based on the operators O of t. Then we can generate all the operators in the bulk, if there's duality, of course. We can generate all the phi of x operators living in the bulk in that causal wedge, in that triangle we draw based on causality arguments out of these O of f operators. And as the people in this paper showed, these O of f operators defined a well-defined algebra, von Neumann algebra, and also the phi operators define another algebra describing the bulk. And in the end, these two algebras, in the case of having a duality, in the case we can draw this picture, carry the same information in some similarity to the previous 1D kind of duality we had, where the two Hamiltonians were describing the same physics. So now, let's assume that we have two boundary regions, one from minus t to t, and a bigger one from minus t prime to t prime. And we can play the same game. We can draw the causal wedges, the two blue triangles, for the two corresponding regions. And we notice that there is a small gray box for which there are some operators, some bad operators that could be generated from operators in the prime should be at t, sorry, from an algebra in the larger region. They cannot be generated from the algebra on the smaller region of the boundary, and also they commute with all the operators that are generated from the algebra, from the small algebra from minus t to t. This means that we could find a function g of t, which is supported in the large boundary region, for which the operators OF and OG, which are the operators that generate the gray region, commute with each other. And the authors of that paper said this maybe mean that we could translate the question of whether we can have an emergent bulk, or whether we could have such a picture on the right, by translating this question to can we find a function g with support from minus t prime to t prime such that this integral goes to 0. And this integral contains this row of t comma t prime function, which is pretty much the average of the commutation of the two operators, one in t and one in t prime, which is actually the function we are interested in. If we take the Fourier transform of this function, is the spectral functions, which actually we will use very soon. And the authors of the paper made some statements and proved some theorems so that they could extract some information from the behavior of these spectral functions and say something about whether we can have an emergent bulk or not. And the theorems they proved, we will care about the first two, is that if rho of omega is compactly supported, then there is no emergent bulk, while if it's full supported and it decays at most polynomially for large frequencies, then there could be a bulk. Of course, this is a diagnostic tool, it's not a strong statement, there could be an emergent bulk, yes.
So can you say what exactly you mean emergent bulk?
That we could have this kind of picture. We could have a boundary described by some operators, boundary operators, and then we could find a bulk theory and a connection between these bulk operators and boundary.
But my question is, what are the data that you start from? I mean, this is saying that there is an emergent bulk. Is it you start with data you start with something which is on the boundary, and you
I start with
whether you can somehow see this as coming from the boundary.
Exactly. I start with a boundary theory.
Okay, you start with the boundary theory.
And I want to ask if there is a possibility for a theory. Later I will have an example for a bulk theory. But yeah, this is the question. We start from the boundary, whether we can have an emergent bulk.
So can I ask you a question on that? So but in the bulk, like, I mean, do you assume some particular geometry, or what do you assume in the bulk?
Here I don't assume particular geometry, but in the paper they discussed about horizon, like having a horizon, for example.
I'm not talking about the horizon. Like, I mean, this cannot work like in flat space, right? So in the bulk,
You
cannot
maybe
be-
imagine geometry.
Yeah.
That's probably what.
I mean, it should be ADS, right? I mean,
It is ideas.
Yeah, already by choosing a vertical boundary, you have that in mind.
It should be ADS.
Yeah, it is ideas. Yeah. So the take-home message of the first idea is that we could use the support of the spectral function as a diagnostic tool to check whether my boundary theory could have an emergent bulk. So now we can move to the second idea, which is searching for dualities in quantum many-body models. So the most popular and maybe well-studied, and people still do works on it, such model is the SYK model, where people have studied many different regimes and and one of them is the double scale limit, where people think that there should be a dual theory related to it. Also, there is a triple scale limit, and people try to make a relation with JT gravity. But under the same logic, we want to ask the question whether we could find another quantum many-body model that could be dual to a gravitational theory or framework of high complexity. And this comes from some work like this, probably the first discussing about these ideas. There were also some follow-ups. And I can give an example of such a framework of high complexity. It's the model of these black hole molecules, where the authors have found some Einstein solutions that form multi-horizon bound states, and they assume like a background of a big massive black hole. And these bound states form complex configurations And of course, they're stable under gravitational and electromagnetic forces. So people have studied this, this configuration of high complexity, and they have found that they have some properties. The energy landscape has exponentially many minima, which means that the systems getting stuck in one of them and need exponentially long times to relax, to jump into the other one. And what people propose for a few years now is that we could find a dual quantum many-body system for these kind of models that are the spin glasses. And the arguments they're using, why we choose spin glasses, is because they have the same properties. So there is not a very concrete, there is definitely not concrete duality statement. There is just the fact that they share the same properties. And to give, thank you, and to give a very brief description of what the spin glass is, it's specific models that they have a transition. After a transition temperature, TC, there is what they call shattering of the Gibbs state. And we can write the Gibbs state as a sum with exponentially terms of ergodic states. And also, they break the replica symmetry. People think that these two are connected. But nevertheless, the result is that these many-body models have the same properties as what people have found for these high-complexity gravitational frameworks. One such model is the SUM-Heisenberg model that we also studied. And it's here we have written it in a bosonic representation. And this kappa just counts the number of local degrees of freedom, how many bosons we have on each side. And we can find this, we can draw a phase diagram. The psi axis is temperature and coupling strength. The x axis is this kappa number, the number of local degrees of freedom. And indeed, there are two phases. After you reach that, you pass this transition temperature, then there is this replica symmetry that is broken, and you have all these properties. So these are the two messages, like the two take-home messages of these two ideas. The first one, I just remind you that we could use the spectral functions as diagnostic for whether our boundary theory has an emergent bulk or is dual, or a dual. And the second one is that people have proposed these spin glasses as a possible dual for these high complexity gravitational frameworks. So what we did was we thought, how about trying to combine these two ideas by finding concrete many-body physics models like the one I showed before, and calculate the spectral function is something that we can do in many-body physics and study its properties. So the first thing we wanted to do is to check this diagnostic tool. It was never applied on a concrete model, so on a many-body model. So we just chose SYK model because we know that in the large Q limit, people think that there is a dual theory or there is an emergent bulk. So also we can calculate everything, we can compute everything analytically. And indeed, we found that the spectral function has a full support, but with exponential decay, not with a polynomial decay as the two theorems of the first idea were proposing. So for the next model we're going to study, we will take this behavior as a benchmark behavior because people expect that the large Q limit of SYK could be holographic. So the next model that we study, so that we combine it with idea 2, is a spin glass model. And again, we want to do the same job. We want to calculate the spectral function of this SUM Heisenberg model for different positions on the phase diagram. Again, this is the Hamiltonian, this is the phase diagram, and what we had to do is we had to compute the Zwickau-Dyson equations and the two extra equations of motion we get from the spin glass parameters, which pretty much control whether we are in phase 1 in the spin liquid phase or in the spin glass phase. And for each one of these points, we have to solve these three equations at the same time, and we can calculate from that the spectral functions. And that was quite a painful procedure to do. We had to start from the spin liquid phase and adiabatically move and cross the transition line to the spin glass phase. So, yeah. So I can show you some of the results for that specific model. So starting from the spin liquid phase, indeed we see this is a log psi plot. So indeed we see straight lines, which is, thank you, exponential decay and full support, which is not something surprising. Now we enter the spin glass phase, and we see that the behavior changes. We see this weird kink appearing and a sudden drop, which we think it's some tendency of compact support. I mean, it's numerics. We cannot, we just, think that this is not, it's definitely not exponential decay, but also we think this is compact support, which means that this area of the phase diagram could not have dual, could not be a possible candidate for these multi-horizon models. We do the same moving vertically. We start from the spin liquid phase again. Again, we see exponential decay. This is not surprising. But now we go to the spin glass phase for kappa between 0 and 1. And in this case, we see that the exponential decay and the full support behavior of the spectral functions remains, although we are in the spin glass phase. So probably this is a regime that we should look a bit more carefully if we want to make any connection between spin glass phases and gravitational theories of higher complexity. So with that, I think, with that, I can just sum up. So what we did, we applied the idea of using the spectral functions of the large N spectral functions as a diagnostic tool to check whether concrete quantum many-body systems could be holographic, could have a dual. And the idea was that these spin glass models, people think that we could somehow connect to high complexity gravitational theories. We found a small regime, like we tested two spin glass models, but only that small regime showed full support, what we wanted as a first step towards a possible duality. But just to be clear, this is of course not a proof of any duality. It's just an indication that we should probably, maybe, if we're interested, look at that specific regime. And there are, of course, many open questions out of it. And I think the most interesting one is the first one that we want to start working on in January. If there could be some duality to this multi-horizon picture, we should maybe search for these singularities. And there was a paper very recently that they were using the behavior of spectral functions in the complex plane, and they used it for SYK, for example, model, and they were claiming that from the position of the poles of this spectral function in a complex plane, you could say a few things about singularities, and naively thinking, maybe we could apply that on that specific regime of the spin glass model. So yeah, with that, thanks a lot, and yeah.
So have you looked at the lower energy effective theory of this spin glass model, the analog of the particle?
No. So this should we do as a future step, and also we should try to find, like in SYK, some limits that we could do stuff analytically. Because after we have solved the Zwinger-Dyson equation, which we could do, then we had to do numerics. And with numerics, I don't know, for me, it's not a strong argument. Yeah, this is, I guess, the natural step, like in that small regime, and also trying to find something to do analytically. Yeah, yeah, thanks. Yeah.
Thanks for making this introduction. In the spin class phase, what distinguishes whether I can have a bulk description or not? Is it the value kappa? So somehow you can have for small kappa a learning description that breaks down and you increase this parameter. Should I think of it what how should I, what distinguishes the region within the spin class phase that has a dual distribution and does not?
We don't have a we don't have an answer to that. We just observe the behavior of the spectral functions. So we haven't thought of what could be the kappa, the meaning of kappa in that possible dual theory, gravitational dual theory. So I can't tell you if it's the kappa or if it's the low temperature that gives this behavior. I can tell you that, again, from numerics, if you go to low temperatures but larger kappa, again you see that that king behavior. So the only regions we see exponential decay in the spin glass phase is for kappa from 0 to 1. But this is not a statement, I cannot make a strong statement that, oh, it's the kappa, because right now we don't have a meaning. We know what kappa means for the many-body physics model, but we don't have a meaning for what kappa could mean for a possible dual theory. The kappa is the number of local degrees of freedom for the many-body model. But only in that small regime we see exponential decay in the spin glass phase.
No, I don't see any, so thank you very much.
Thanks a lot.
So our next speaker is who's going to tell us about the theory of dissipative dark matter in the book.
Okay, hello everybody. I'm really happy to be here today and to have the chance to tell you a bit about work I did recently with Joseph Pradler on the theory of dissipative dark matter. But before I'm going into technical detail, let me give you a big picture, because I know that we are a really diverse audience today and we switch again some topics, so let's be sure that we are all on the same setting. So we all know that dark matter is only observed through its gravitational imprint from the galactic scale to the cosmic microwave background. And then the question, once these observations are done, is what is a good dark matter candidate? And the answer is actually a lot. So it's a landscape that spans many orders in magnitude in mass. But for this talk, we are going to be interested in what is called a hidden dark sector, which is that we completely neglect any interaction with the standard model particle. Even though there is all of these dark matter candidates, cosmological picture is quite simple. During structure formation, we want a dark matter that is cold, that is electromagnetically neutral, and that is collisionless, at least at large scale. Indeed, this picture of collisionless and cold dark matter is really successful on large scale, so we call a large scale bigger than a few megaparsec. But when we go at smaller scale, the n-Bose simulations that we use to do prediction is actually showing some long discussed discrepancy with what we actually observe. This is what we call the small scale problem. This small scale problem could be the hint that maybe we should drop this idea that dark matter is collisionless on this smaller scale and why actually. So let me show you an example on this small scale problem. So in dwarf and low surface brightness galaxy, the lambda core dark matter predicts that the central density of this dark matter halo is going to be cups. However, when we compare to the observation of rotational curve, we observe some more core inside halo density. And one way to reconcile this observation in the prediction is to make the assumption that the dark matter is self-interacting with itself, because through this self-interaction you are going to have some heat transfers that are going to soften the inner density profile, and so we can find back some more core-like density profile. In order to have a prediction that is consistent with observation, you need actually a cross-section that is quite large. So to give you an order of magnitude, this is way larger than the usual weak scale. And you could have two kinds of self-interaction, or through this kind of contact-like interaction, or, which is way more handy, by allowing that your self-interaction is also mediated by a light mediator. And in that case, you obtain a velocity-dependent cross-section, which is nice because it means that you can also, in a way, parameterize it so that at larger scale you don't have the self-interaction because you want something that is collisionless. This self-interaction, even if you put aside the small-scale problem and you don't want to enter into this discussion, it's nice because in the top of self-interaction there is some other effects that are coming that are important to study, which are dissipation. Indeed, directly inside the self-interaction there is some built-in dissipative channel. So if your mediator is light enough, you can imagine that it's also emitted during your self-interaction. But you could also build in a theory with a larger mediator. This is what you prefer, but in that case you could also have this kind of dissipative effect, but you need to add an additional light particle to your theory. Why these dissipative effects are important? Because actually they lead to some cooling effect inside the small scale structure and the halo that have been intensely investigated in more complex dark sector. That are based on Baronin-like description of the dark matter, so which, when you compare to this really simple model, have nothing to compare. But still, I've shown to have many impacts, from the evolution of supermassive black hole to, why not, the formation of a dark disk, and to the formation of history of dwarf galaxy. And between this really simple scenario and the more complex dark matter, what is actually important is the net energy loss that you are going to have through your dissipative processes that you can already infer through this minimal dissipative model. So for this talk, I'm going to focus on this minimal model, which is also the focus that we did on the paper I would like to present to you now, in order to obtain dissipative rates, so we could see what and where will be the impact of this dissipative dark matter. So up to now, we have studied a set of 6 dissipative dark matter models with our dark matter candidates that were ranging from scalars that could be real or complex, and to fermions that could be Dirac to Majorana. We considered some mediation from scalar to gauge with the emission similarities that could be scalar to gauge, and 2 regimes of mediating force from long range, so a mediator that is having a really light mass, or short range, so a mediator with a really heavy mass. For this talk and in this work that I'm presenting to you, we have focused on the Born regime that is actually delimited by these 2 really small parameters. And why we did that? Because in the Born regimes, initial and final scattering state reduced to plane wave, which means that we can neglect non-perturbative effects, and we can actually study our dissipative effect and our self-interaction using 3-level quantum field calculation. So it means that our 6 model can be described by these 3 really simple Lagrangian, where we also studied some self-interaction, but the overall detail of the coupling are not that important for now. Just note that in the case of a heavy mediator, you need some additional particle in your theory. You also have some primate coupling that need to be added to this Lagrangian. These Lagrangians themselves, in the quantum field theory language, translate into a set of large but finite number of dissipative channels that we need to evaluate if we want to obtain an emission amplitude. Just to note why I say large, because each dot here, so each orange dot, corresponds to where a particle could be emitted. So you imagine that already this diagram corresponds to 4 amplitudes, so the emission amplitude can become quite lengthy and heavy numerically to evaluate. However, we are lucky because we want to apply our result to a small-scale structure, where the velocity of dark matter is low, such that we're in a kind of a non-relativistic setup. This non-relativistic setup leads to naturally a separation of scale in the center of mass frame of the scattering between the initial momentum of the two particles that scatter and the particle, the energy of the particle that is emitted. And this is actually nice because applying the separation of scale, we can actually evaluate our really lengthy emission amplitude as by expanding it with respect to the initial velocity of the dark matter candidates that collide. And we obtain some compact analytical expressions that are more easy to read. And also each contribution of this different channel to the emission amplitude are going to also be sorted by their dependence on the velocity. This non-relativistic framework is also interesting because it's allowed to apply our physical intuition to a process that I'm sure most of you already know, the Bremsstrahlung, so the emission of a photon in an electron-electron or electron scattering processes, where the emission amplitude is usually expanded in terms of multipole. And this multiple expansion is controlled by the ratio to coupling to mass of the particles that scatter together. And so dipole part of the emission amplitude usually dominates, but cancel in the case if you have the two particles that have the same coupling to mass ratio, and in that case you must look at quadrupole emission. It is important to note that between the dipole and the quadrupole there is a velocity suppression, which means that actually the power counting that we apply to our dissipative channel allow to exactly find back these dipole and quadrupole part of the emission amplitude for all of the models we have investigated. So now that we know a tiny bit more about the framework, let me tell you what are these dipole and quadrupole part of the amplitude characterized by. So for all of the models we have studied, and for the long-range mediation regime, the dissipative channels that participate to the dipole emission amplitude correspond to this diagram, so an emission from the external leg. And at this order, we realize something really nice, that the dipole emission amplitude is actually showing a model-independent kinematic part time dipole prefactor that is common from all of the models we studied. Which means that actually at dipole order, the detail about the nature of the emission or the dark matter candidate is completely velocity suppressed, so you obtain a compact form that is only dependent on your coupling and on a small kinematic part. Once you have the same coupling to mass ratio, of course, this part cancel. You need to go at quadruple order. In that case, there is model dependency that arise that you can see here by this alpha beta in the kinematic part of the emission amplitude. However, the non-relativistic regime is giving that this model dependent part are still happening pairwise, which means that for gauge emission, you are completely blind if you use a fermionic dark matter or a scalar dark matter, because spin effects are suppressed in our regime. And same for fermionic like Majorana or Dirac dark matter candidate with scalar emission. because you have that also the annihilation channel are also superset in the non-relativistic regime we are in. So also for the other kind of mediation, so the short-range mediation, the additional conditions that you have on the mass of your mediator lead that the different dissipative channels are going to be organized in a different way in the emission amplitude. However, we still can end up with the same conclusion that dipole emission shows some model independency, which is not the case for quadrupole emission. So up to now, what I presented to you was the case of massless emission, but nothing forbids us to imagine that the emitted particle is actually carrying a small but allowed mass. In that case, for vector emission, it means that you need to add the longitudinal component to the transverse ones that you have in the massless case. And we also have found a really nice relation between this longitudinal component of the emission amplitude for vector emission and the component of the scalar emission, both for fermionic and scalar dark matter, which is that there is some common kinematic mass-dependent correction in both cases that appear both at dipole and quadrupole order. Without entering too much into the detail of the calculation, we can trace back these equalities actually to the fact that we use a conserved current, and by applying the word identity to our longitudinal component, which means that this nice identity does not hold for the case of the transverse mode in vector emission. So if I have to resume quickly, everything I just told you is that even though we started with 6 really different dissipative models, the fact that we are in a non-relativistic framework leads to some model independentiator inside our emission amplitude and at different level. And by example, at dipole order, you end up with a really common expression for the emission amplitude, while at quadrupole order, you still have some model dependency, but you end up with 3 expressions instead of 6. One way to test our expression, and also one nice quantity to derive, is the so-called energy differential cross-section, which is the differential cross-section multiplied by the energy of the emitted particle. And let me just flash you quickly some results about this. So at dipole order, you see this model independencies, as this is corresponding to the energy differential cross-section of our 6 model, this brown curve, that is the same for whatever dark matter candidate you choose. And we also have obtained this really nice compact analytical expression that we have compared to the full QFT results. So by taking all of these different dissipative channels, integrated numerically, that correspond to this black dotted star, and you see that our dissipative, our simple analytical formula of the dissipative energy differential cross-section is actually in perfect agreement with the full result. At quadrupole order, in agreement with what I told you at the amplitude level, for here this is for the scattering of distinguishable particle, model dependency arises, but we still obtain some really nice compact expression for the energy differential cross-section, which again are in perfect agreement with the full numerically integrated result. And this model dependency can also just be parameterized by this beta and alpha parameter. And just to mention, quadrupole emission also corresponds to the case where you have the scattering of identical particles, which doubles the number of dissipative channel contribution, so change a tiny bit the expression of the energy differential cross-section, but you observe, of course, the same tendencies that model dependency also arise, so you cannot anymore neglect the nature of the dark matter particle or the particle emitted. So up to now, I tried to give you an overview of more the microphysics part of the work, but what ultimately matters is all these microphysics processes are actually becoming inside more macrophysics microphysics system, which is for us a dark matter halo. And to do so, we can actually imagine that our dark matter halo is a kind of a non-degenerate Maximilian gas that is composed of our different dark matter scenario, which makes the link between this initial velocity, from which we have done the expansion of the amplitude, to the temperature of the system. And if we do so, the important observable is the so-called energy loss rate, that corresponds to the energy lost by the system by unit of time, so that completely depends on the microphysics. This dependence on the microphysics means that the universalities that we found at the level of the amplitudes and the energy differential cross-section, we are also going to find it at the level of a microscopic system. Indeed, without any surprise, we have found that the energy loss rate for 6 model was actually composed of a dipole part plus a quadrupole part, with the dipole part being the dominant component of the emission, but of course in the case this part cancel, you must rely on the quadrupole emission part. We have compared the two mediation regimes that we have studied, so light mediator and heavy mediator, and we have found that in a realistic physical system where you would have both, the long-range processes dominate the dissipative dynamic, as the heavy mediator processes are highly superset with respect to the temperature. We also have checked how much this model dependency was arising at the level of the energy loss rate, and actually it's quite mild. So at each multiple order and for each mediation regime, this difference between the dissipative scenarios that we found at quadruple order just appear to be mild, so 1 or 2 order of magnitude for comparable coupling and mass. Which is actually quite interesting, because it means that the energy loss rate, actually, even though you start with a quite different model, you end up with something that only depends on the mass to charge ratio of the dark matter model you started with, on the maybe mediation regime, and on the velocity scaling of your halos that correspond also to the temperature. We also have checked what will be the effect of adding this mass to the energy loss rate. And actually, this massive emission allows to naturally modulate the dissipative rate, because if the mass of your emitted particle is larger than the temperature of your system, your dissipative effects are going to be velocity suppressed, which means that if you have a mass that is bigger than the temperature in a dwarf galaxy, your dissipative effects are going to be completely suppressed, while they will stay untouched at the level of larger structure like a galaxy cluster. So to summarize on this work, we actually work out a kind of a catalogs that are based on this dissipative model, where you can directly read out the energy loss rate and the energy differential cross-section that can be applied and adapted to a wide range of coupling, mass, and mediator property. Of course, for us, the application was halo, this halo model, and self-interacting dark matter, but you could see, well, that you can also adapt it to whatever kind of emission processes you would like. And in general, to conclude and to maybe again give a big picture, there is some discrepancy in the small-scale problem of the lambda of dark matter that could be, or not, a hint at some missing physical mechanism. This is a perfect motivation to imagine that the dark matter could be self-interacting on this smaller scale, and in that case you have interesting effects such as dissipation. And if this is the case, it is really important to have a unified treatment of these dissipative processes around a large set of minimal model, and this is what we started to do with this paper. And so in this talk, I try to show you that when you start even in a perturbative regime, using simple QFT, you can still reconstruct the dipole and the quadrupole piece of the emission amplitude. That's the case of massive emissions that is usually not studied because, for example, in QED, a photon has no mass. is also leading to some really interesting macroscopic effects. And I try to stress that the fact that on the non-relativistic framework there is some model-independent features that arise, which we found back also in the energy loss rate. So as an application, we can use our result, of course, to constrain the parameter space of the self-interacting model and also to the formation of small-scale structure. And our next step will be to this time drop the idea that we are in the Born regime and to study what happened to our physical rate if we include non-perturbative effect for this model. Thank you very much for your attention.
Thanks, Ganas, for the nice talk. I have a couple of questions. First is, okay, you spoke about dissipation in the context of self-interacting dark matter.
Yeah.
Is it necessary, I mean, to have self-interacting dark matter for dissipation, or I can see it in a general context?
I mean, for the context of this paper, you need the self-interaction first. Oops.
Yeah, this is clear.
For sure, because we take them as really being a tree-level expansion of your self-interaction. In other more complex dark matter models, they base themselves on a baryonic lag sector. So really this question of dissipation appear in a completely different way. You have bond state formation and you can have these dissipative effects that appear differently. But for this context, for minimal model, you need to have self-interaction.
All right. Unless you want to say something about
yes,
this.
yes,
Yes, go ahead.
The question was, well, if you did it by baryonic, the other, this is still self-interaction.
Yeah, actually.
So either way, you would need
Yeah.
self-interaction. I'm done.
Yeah, I think on the top of my head, I cannot imagine right now something where you don't have this interaction, but I'm not a specialist of baryonic effects, so it may be a way to do it that yeah.
Yeah, okay. And now the second thing is, what would be the smoking gun to observe such to verify such a model?
So it's completely depend on what kind of structure you predict. So with our results, we only predict when could this dissipation happen and where inside the halo. In more complex model where they take into account more microphysics, so for example the formation of supermassive black hole and or of a dark disk, they have different kind of smoking gun, and that would be mainly, I guess, the dynamic of the baryonic matter inside the system. Because if you have, for example, a dark disk, you will not have the same way the stars are going to move inside your halo. So it's really model dependent. This smoking gun is also really dependent on what kind of compact object you are going to predict. And yeah, I can, if you want, we can discuss it more. I can
Yeah,
also.
yeah, we can discuss later, definitely.
Thanks for the talk. So in this whole range of possible dark matter candidates, could you maybe motivate a little bit more why, if there are any arguments, physical arguments, why focus on this particular mass range and why particularly this hidden dark sector candidate here?
So for hidden dark sector is because we don't need any interaction with the standard model. So you really want a self-interaction is something that only happens inside your dark matter, and you don't need any interaction with the system. This mass range is motivated because you need quite a large cross-section in order to have some observational effect. And in order to have a cross-section of this range, you need a mass more or less of the level of the GeV.
You maybe go to slide number 5. You mentioned you started 6 different models.
Yeah.
If I am naive about the type of dark matter candidates and the type of mediators, so I would count 8 models, like in a sense of, the dark matter is scalar terminal. The mediator is gauge or scalar. The force is long range or terrain. So why is number 6?
Okay, so it's me who choose it because this is the way in my head I separate them. So you first choose. You first choose the mediation regime, so you have long range or short range, and beside these two mediation regime, you can decompose this different parameter into these 6 theories. So for gauge emission, you could have both gauge emission with fermionic dark matter or with scalar. For scalar emission with this scalar dark matter, you can have both complex or real scalar. And for fermionic dark matter, also you can imagine both Majorana or Dirac-like. So this is the way what I say 6 model, I'm referring to this 6 decomposition. And of course, after you need to apply if you want to be in a heavy mediator or light mediator limit.
Okay, so let's thank our speaker again. So our next speaker is Evangelos Soulakidis from the University of Iceland, and he's going to tell us about the city-bar connection.
Hi. Thank you very, very much for having us here. It's my first time actually in Athens. I'd like to tell you a little bit about the city-bar program and how I view it. So this will be joint work with Alexia, who's also here. She's giving a talk tomorrow, and a paper that I published last year. I understand that I have given instructions to keep this as open as possible to everybody, so I'll try to do my best. But if not, please feel free to stop me and ask me as many questions as possible. Okay, so this is very schematic. Here are 2 colleagues, one experimentalist and one theorist. I use the Greek there because if I use the T with the red hat, it would be somewhat edgy nowadays, if you know what I mean, but if you don't, it's fine. So experimentalists either look up or down. I mean, they look up, they see black holes and stars and stuff like this. They look down, they see atoms. They look straight ahead, they see humans. So they say, I observe this, this, and that. And they then go and talk to theorists, us, to say, okay, can you explain what I see here? And more or less, very vaguely, we have here an axis with a scale. We say that the UV, which means very, very small distances, very high energies, is there at the bottom. Usually, people do the opposite, but I find it more natural to have it this way. So we have Lagrange's describing physics on different scales. The UV, you can forget about gravity. You can have the standard model. As you flow up in the IR, you have gravity. You forget about the standard model. And so the first thing I'd like to tell you is where this program is placed here. And it's exactly in the deep UV and in the deep IR. This is a little bit counterintuitive, but a very naive way of seeing how these two are connected. If you just take 1 over UV, you end up in the IR. Okay, a little bit more motivation here. So this whole program is about quantum field theories and how to deform them. So how do you deform quantum field theories? We have a very good notion of how to do this. You start from here some undeformed seed theory. Can you see it? Yeah, you can see. I'll call it L0. And then you go to your deformed theory by turning on a coupling. It can be relevant, irrelevant, marginal, whatever you like. At this point, I haven't specified anything. Times some operator. And more or less, this is where most people would stop. That would be the end of the story. So the question that we're asking here, and it's really out of mathematical curiosity of why to do this, because you want to map out what you can and what you cannot do in principle. Maybe it's useful, maybe it's not. The question is, can I do anything else with this? Yes or no? And to see that you can do slightly more, you can just take one derivative with respect to lambda. And then you end up in an equation that looks like this. In the field that I made, people call this a flow equation. I don't know why, but this is how they call it. In principle, it's a PDE, and it's a very sick PD in some sense because it only has one initial condition. The initial condition, that is, if you turn off your coupling, you should go back to your antiform theory. So how do you solve this equation? If you go on the left, yes. So your operator would depend on some fields. You can just directly integrate this equation out. You end up back where you started in the previous slide. However, you can do something else, something new. And that is to consider an operator that has some implicit dependence on the deformation parameter lambda. Then it's not trivial to solve this equation. So then the question is, what is that equation? And what are actions that satisfy this type of an equation? Moreover, which are the types of operators that have this particular dependence, implicit dependence on lambda? And the only data that I've given you so far is that you have some undeformed theory, some deformed theory, and pretty much that's it. So you understand that this operator, at the end of the day, should be some implicit function of the deformed functional that I'm trying to find in the first place. So this is very counterintuitive. You can see it. Oh, I can use this. You can see this implicit dependence of the deformed theory that I'm trying to find in the first place. So how do you solve an equation like that? And then, more importantly, what is this deformed theory and why should we care about it? Hopefully, you'll be convinced by the end. Okay, already small review. You give me some L0 and an operator, and I give you some deformed theory by just solving the flow equation. L0 can be anything. It can be an interacting theory or a CFT. You know, pick your fights. Whichever one you prefer to pick. A more important question is, what are the types of operators that have precisely this dependence? And for the sake of the argument, consider the stress tensor for a minimally coupled theory. Here, the F would be my Wilbein. I work with the first order formalism because it's more convenient for what I do. And if you calculate the stress tensor for a theory like this, you see that it depends on the deformed theory, lambda, and its first derivative with respect to the background. So it fits precisely in this category of operators. Still, this object has two free indices, so you need to contract it with something if you want the Lorentz invariant theory. You can apply this whole program also in non-relativistic theories. You can extend this by using Cartan or whatever your favorite geometric framework is. However, we have some logical here the rescue that says, okay, if you want to pick an interesting operator in 2 dimensions, you should consider really the determinant of the stress tensor, and that is what we divided. It's the determinant of a stress tensor in 2 dimensions of a quantum field theory. And it's an order 2 polynomial in terms of the stress tensor, which is a particular function of just the trace of the t and trace of t squared. So here's where the first problem comes. This deformation is irrelevant. So how can we do anything with it? Because it's in principle non-normalizable. For some magical reason, this object is very well defined at the quantum level. And it is protected. So the beta function doesn't get any corrections. It's very weird, but it is the fact of life. So this has many properties, this operator, but I'm not going to discuss them here. I'm just going to try now to solve the flow equation with an operator that looks like this, or it's in general functional of your stress tensor. The price is always at the end again. Okay. So here in the middle, you have your operator. This is T bar in our case. I'm shifting to an action picture now because it's more convenient for me. And here would be some undeformed theory. The stress tensor, T bar is for 2 polynomial at the scaling dimension, and I'm looking for the deformed theory. So one way to find the deformed theory is 2 standard perturbation theory. As I said before, this is a PDE that you need to solve. So you expand in small lambda, turn the crank, and hopefully you find something that is useful. Or you can just guess the answer. So that's the method here on the top. That's the answers method. By the way, many of these things here might not make sense to you. Maybe they will. I'm not going to explain in detail how they are connected, but I'll just tell you that all these things are related by some trivial calculations. So, as I said, this is the answer method here at the top. You can just guess what would be the deformed theory. plug it in your flow equation. If it satisfies it, it's good. But this is a perturbative approach to solving this problem. You can consider, and Tubolsky, Gorbenko, and friends have shown that you can take this theory, your undeformed theory, you can couple it to flat-shaped gravity, which is the type of gravity that lives in 2 dimensions. And that is equivalent to taking the T-bar deformation of a flat theory. Equivalently, you can couple it to a ghost-free massive gravity, where the mass of the graviton is precisely the one that DRGT gravities predict. This is the Ram-Cavadad-Gentoli, which ensures that there are no ghosts present in your deformed theory. There is the random geometry framework by Hardy, where you can think of this deformation, this particular deformation, as a Haber-Stradonovich transformation, where the auxiliary field is again spin 2 field. So you see gravity enters very naturally in the game here, even though we're talking about quantum field theory. And there is a very, very intricate structure where you can get to your deformed theory by a very sophisticated field-dependent change of coordinates. These are the main approaches to find S lambda. However, there are also connections to radial cutoff holography, ADS3 in that case, because we are in two dimensions of field theories in 2 dimensions, and also in string theory. The most prominent example is if you take just a scalar boson and you try to T-bar deform it, you immediately get an Avogadro string in the 3-dimensional target space. 3-dimensional target space in static gauge. And if you want to learn more, I don't know if you can tweak this, but later. I can tell you more about it. So out of all these approaches, the simplest one is the massive gravity one, because the rest essentially fall out of this particular formula in some limit. So I'll talk about that a little bit more. So in principle, any deformed theory by this particular deformation can be brought in this following form. This is your undeformed theory. It lives on a Hilbert E, fly-by Nash actually, in 2 dimensions. And I couple it to a ghost-free mass of gravity, and that's the mass term of your graviton. Lambda is my relevant coupling. However, in the mass of gravity literature, 1 over lambda is the mass of your graviton. So you see, we went immediately from the UV all the way up to the IR in some sense. So there are 2 gravitons. However, at the end of the day, I'm doing quantum field theory here. I don't have multiple backgrounds flying all over the place. However, the prescription tells you just take your S0, you couple it like this, and then you try to integrate out your E if you can. That's not a given statement. And then your field theory would be the deformed theory, limit or your background F. This is pretty much it. This is how you get to the deformed theory at the end of the day. However, it's not going to be very convenient over what I will do in a bit. So let me rewrite this particular term in a more convenient language. So I will define y as the inverse of F times E. These are again 2 Wheelbeins, so they're invertible. I can do that. And then I can rewrite this particular mass term in terms of this y variable. So it's a quadratic polynomial now in terms of y. And it's a particular choice of some mass term g, in principle. It's a particular limit of that. And to remind you again, what's the corresponding operator responsible for this? It's just a particular quadratic choice of this functional f for an operator. So you look at these expressions very closely, given that something like this should be true, and you find out that there's a very nice duality between the gravitational dynamics and the field theory dynamics. And that's not a correspondence in any sense, it's the direct equality. So if you take one derivative with respect to lambda for your gravitational dressing, you see these y variables are only functions of your background variables. It's precisely equal to the operator that you should deform your field theory with. We still don't know why this equation is true, but it is. And describes very nicely the duality between gravitational dynamics and field theory dynamics. This is all classical, by the way. However, in D equals 2 and 4 bar, you can push this to the quantum world with no problems, or at least with not serious problems. So, more or less, this is all review. So, what did we do? We thought, okay, the most natural question is to ask how much of this structure survives some uplift in higher dimensions. And to do this, we started with the equation that I had exactly here. So this is 2 equals 2. You see tractates at y to the power of 2. This tractates at t to the power of 2. In these dimensions, this equation follows this particular format here. And this is actually a result of a theorem from linear algebra. It's called Cayley-Hamilton theorem. And it says that if you have a d by d matrix, only the first d powers of that matrix are independent of each other. So necessarily this equation takes this form. Okay, we still don't know what the operator would be in higher dimensions than 2. So in 2 dimensions, the only thing we have, the only guiding principle we have is that in 2 dimensions f was fixed to be polynomial over the 2. So in d dimensions will be expected to be polynomial over the d. Immediately this fixes the scaling dimension to be minus d. Still, this is an irrelevant information from a field theory point of sight. So in the gravity side, 2 dimensions again, g was picked to be polynomial over the 2, and we'll pick it in d dimensions to be polynomial over the d. So we make these two answers. This, if it's a polynomial over the d, it has a lot of free coefficients there because these are polynomials. However, this equation, even though it's one equation, it completely determines all of them. So you get at the end of the day a unique solution. Okay, okay, let's look how the solution looks like. So in d dimensions, g takes precisely this form, and we had no idea what this particular mass term is for a graviton. And after almost a year of looking, we realized that this particular mass term is a very well-studied mass term in DRCT gravities. It was proposed by Hassan Rosen in 2011 in 4 dimensions, and it's a ghost-free. It's called ghost-free minimal massive gravity. So somehow, for some reason, these types of deformations know about massive gravitons. We don't know why. We just observe that this is true. On the gravity side, it's in d dimensions. So you just take this g, you couple it to your S0, and then you try to integrate it out to find your deformed theory again, if you can. Elements of that also appear in 3 dimensions. You can look at this paper by Bergship and friends. In the field theory side, what we say is that coupling S0 to G is equivalent, as I said, to deforming that S0 with an operator that looks like this. So in 2 dimensions, we get dizzy bar. That's good, I guess. In 3 dimensions, we get the quadratic piece plus a cubic correction, either no more. In 4 dimensions, we get the quadratic plus a cubic plus a quartic, and the pattern goes on. Actually, in d dimensions, this truncates at the order d. T equals t to the d power. So what is nice about this expression is that the quadratic part matches precisely what you would have gotten from holographic normalizations of just empty ADS. And we still don't know why this is true. However, we find that these 2 approaches match at quadratic order. However, we have corrections that holographic normalization cannot explain, or at least we don't know how to interpret them in that setting. Okay, we could have made stop here, make claim victory here. So already you see I've connected via this program some gravitational dynamics and some field theory dynamics, and I'll show you. Oops. I'll show you how this also extends to mathematics now in a bit. So we could have stopped here. However, we've said, okay, we have all this framework here. What can we do in d dimensions? This was in d equals 2. Can we get some of these results in d dimensions as well? Because at the end of the day, this thing would sit at the top in 2 dimensions at least. So indeed, we found that one can retrieve the random geometry framework in higher dimensions, and you can think of it as a very sophisticated change of coordinates. Mentioned before, we get an operator that matches quadratically to the Carl ADS t plus 1 story. However, 2 things that we are not able to do was that see this if this flat JT gravity picture exists in higher dimensions, that would be very interesting. And also, d equals 2, we had strings, so the very natural thing to assume is that you might get some dynamics of p-branes in higher dimensions. However, we still do not know. Okay, so what? Okay, so what? I have some dynamics here between gravitational and field theories. I have some deformations. So what can you do with this? What can I calculate that I could not before? So Seth in France in 2019 looked at the T-bar deformation of just pure electromagnetism in D equals 2, and they found that the resulting action is actually a hypergeometric function. So we did the same with Alexia. We added a potential term. So we did it perturbatively, and we did it exactly using the massive gravity framework. And since these two expressions should match, we managed to extract something quite deep. We managed to find out this very, very intricate sum of regularized hypergeometric functions has a closed form expression. If you don't believe me, you can just take a picture of that and go to your favorite mathematical file and check it. But we put this a lot of stress tests on this object. So if you expand in small y both expressions, this answers a very old mathematics problem. So there is, I guess, I didn't know about this, but we found out eventually that there is a search for expressing hypergeometric functions in terms of radicals, and we found the infinite extensions to that particular program there. We also have closed form expressions of the infinite sums. So there is also a connection to mathematics, it seems. And I have 5 minutes, which is good because I'm going to the conclusions. So to conclude, so stress tensor deformations seems to be an interesting research topic. At least we think so. We find many connections in many different fields, but still it's very early to say if this is something more serious or no. And very, very briefly, the seed theory deformed by some operator F amounts to copying that particular theory with the mass of the graviton represented by G. We found a deformation of order D that extends previous holographic results. We recover other formulations successfully. So far, we haven't had any conflicts with any other formulation. And we provided a concrete connection to algebraic structure of special functions. Thank you very much.
So what will be your next steps?
In this program, you mean?
Yeah.
I'm not sure, actually.
Okay.
We're trying out to see if the mathematics aspect of the story actually makes sense to some people. And we try to extend this to non-relativistic frameworks and see if we can get something useful out of it. But other than that, yeah, I'm not sure, actually.
What do you mean non-relativistic framework? Would you have in mind?
Newton-Cartan, for example.
Oh.
You can do this for Newton-Cartan. Actually, if you look at the stringy picture, the Newton-Cartan appears they're very naturally. But it's still very early to tell if it's useful or not. Yeah.
Okay, maybe then I can. So very non-educated question. At the beginning, when you started with the deformation, can you go to the second slide?
Yes.
Just for me to understand what's happening. Right, next one.
Yeah.
Right, yeah, perfect. Yeah.
Okay.
So it seems that the crux is this new way, right, where your operator depends on the parameter. So what is it? So why?
It's a mathematical curiosity at this level.
So typically we have parameters in the Lagrangian, and then we deform the Lagrangian that we have with a parameter plus an operator that depends on P.
Yeah, that's the old way.
So I have some intuition about it. It's the parameter of the theory.
Yeah, exactly.
So
that's the old way.
Right. So how should I think of this deformation now? What's the?
You can still think of it.
The wrong coordinates, and that's why it's screwed up, and therefore, or what's happening?
Not necessarily, no. If you can think of it in this way, but you just don't have a thing that truncates a leading order. You have a power of lambda corrections that follow if you use this definition. So you keep getting more and more and more terms. That's why you get the Navigator string.
So it's not some power, so to say, it's some analytic function of the lambda.
Not necessarily. Well, it depends on the operator in the case you're studying. But yeah, it's very counterintuitive. This I agree.
This question starts mine.
I can give you, for instance, as an example, some operator which has some lambda dependence.
Explicit or implicit?
Explicit.
Explicit? They don't get this. It needs to be implicit.
So if I give you explicit, then probably you can integrate.
Yeah, you can integrate.
Find some of that. Then what could be different with that? This is what I'm trying to do.
This thing, if you have an explicit dependence, you don't get an infinite series of corrections.
I can have you, I don't know, I can give you an operator which has some limit for lambda 0, and then beyond this has some Taylor expansion lambda.
Infinite expansion.
Infinite, yes.
Okay, yes.
Then you can probably integrate it.
Yep, yep.
And find something. Yeah, I don't think it would be the PT bar. It could be maybe what's different here. I'm trying to.
You can do this. No, you're free to do this. Yes. But then you have to see if you can interpret it in some way, in some useful way. But in principle, you're free to do everything you want. But yeah.
And when you say implicit, you mean the difference between implicit and explicit? For me, it would mean that implicit that phi depends on lambda. Is this what you mean?
Not necessarily. Implicit is that it implicitly comes. The implicitness is in the deformed theory that you try to find in the first place. So if O is so this is lambda. This is L of lambda. That's O. Plug it back in there. You see that there is an implicit lambda. So implicit dependence of lambda that only comes through L. It could also be through phi, but then that would make your life miserable. These are PDEs. I mean, the resulting equations you get are nonlinear, highly nonlinear PDEs. So the fact that we were able to get a solution that matched something that somebody else did was very surprising to us in the first place.
Sorry, can I add something? So I'm going to talk about the QI on Friday as well, in the 2 dimensions where a lot of even though certain things are easier. But one thing that we didn't really, we haven't fully understood in our work, and I think it's a big question, is the notion of locality of fields. So we have a theory that is not UV complete, that has, where the degrees of freedom are extended particles, essentially, so you have this length scale that you're introducing by the lambda, and then you try to talk about fields in this theory. And usually we like to talk about local fields, and that is something that is a difficulty for us as well. So I don't know, in this context, do you understand anything about that?
What do you mean by local?
Maybe point light with I don't know, fields that commute with each other if in regions where they are not causally connected.
Okay. I'm not sure.
This field that you're talking about in this abstract way that is constructed in this way, would it have some good properties?
This is still classical.
Yeah.
This is still classical in higher dimensions. We don't know how this works out in the quantum world. But I have a problem when people use locality in the language of PT-bar, because the prime example that they use is that, the Navier string is not a non-local action. But everybody that I ask seems to think otherwise.
Right.
So I'm not. I'm okay. Maybe we can discuss this about later.
Yeah, well, I don't know. I don't want to make it wrong and wrong, but in the context in which we studied this is quantum field theory in 2 dimensions, a massive quantum field theory in 2 dimensions, perturbed by PT-bar, and integrable to start with. So in this context, there is something called a form factor program, where you can compute matrix elements of local fields by solving equations. Essentially. So one thing we tried to do was to say, okay, if we deform the F matrix in the way PT-bar prescribed, can we still solve those equations for the field? And the conclusion is that it doesn't look like, but we also think probably the equations are different because the underlying assumption of these equations is locality in the way I defined it. So I just was wondering if you had any insight.
Yeah, I don't know a lot about the form factor program actually.
Okay.
Maybe I should learn more about it.
Well, you will hear something on Friday. But thanks.
Thank you.
Okay, I think we can thank our speaker again.
thank you, Eliani, and thanks a lot to the organizers who gave me the opportunity to give a talk in this very nice workshop. And so the goal of my talk is to tell you a little bit about Carolian conformal dynamics. What is this Carolian word that maybe some of you have already heard before? That is a particular case of non-Lorentzian relativity, and it's going to be based on this work that we wrote in collaboration with Adrien and Marius, both in Polytechnique, or also here in the audience, and Mathieu Villat, that is currently a postdoc in Mons, and which is hopefully going to appear soon in PRL. And my goal for this half hour is to convince you that non-Lorentzian dynamics, such as Carolian, also next to its cause in the Galilean world that you are mostly familiar with, is interesting to study, and it pops up in very different situations, ranging from condensed matter physics to here an application to flat holography. So let me start a bit slowly with an object that I think most of you are familiar with, because we also saw it in the previous talk, which is a stress energy tensor or energy momentum tensor. So if you have a Lorentzian field theory that is invariant under the Poincaré group, you can always define this T mu nu, which here I wrote in the case of a two-derivative field theory, which is going to be on-shell conserved when you go on-shell for the fields phi alpha, and you can make it symmetric thanks to an improvement. If you also have a system which is scale or conformal invariant, there is a further improvement that you can do, which makes this guy also traceless on shell. So this is one way to compute the stress tensor. There is also another way. If you take your theory and you couple it minimally to a background metric, in that case, you can take the variation with respect to this background metric and you obtain an object which is already symmetric. It is conserved this time by virtue of diffeomorphism invariance of the theory. And in case that you have, let's say, no Weil anomaly in the game, Weil invariance of the minimally coupled, of the conformally coupled theory will ensure that it is traceless. So these two statements are very similar. In fact, let me take the opportunity to highlight this work by our colleagues, where they show that in case you are in a flat background, the two constructions are equivalent and they give a geometric origin to the improvement terms. But so I'm just flashing this in order to introduce the first main character in my presentation, which is the stress tensor. But now I'm going to move to a different realm of non-Lorentzian relativities. We heard a lot of times the term non-relativistic regime. I don't really like this term because if you take a regime where, let's say, the effective speed of light goes to infinity, so you consider systems which move much slower than the speed of light, your system still enjoys a form of relativity, which is Galilean, right? So you take the large C limit, you end up with a Galilean system. You can also do something completely crazy, take the opposite limit, and then you enter the realm of Carolian physics. Okay, pictorially it looks a little bit like this. When you send the speed of light to infinity, your causal light cone collapses to the spatial plane, and instantaneous propagation is allowed. But in the opposite regime, your light cone closes, and therefore the locality issues become a bit more subtle. So one way to think about this is that you have C, the speed of light, or the effective speed of light of your system as a parameter, and you're going to move, let's say, in your parameter space to explore different regimes of Lorentzian theory. And this has been done in many, many examples by now. And the role of the conservation equations, or I will argue that you should rather call them evolution equations in that case, for both Galilean and Carolian theories is increasingly studied. One particular useful application of Carolian physics is in the so-called flat holography program. So what should I do?
30 seconds.
Press any other button to cancel. Thank you. Yes, so Carolian physics is the Carolian symmetry is the useful symmetry group that you can use to describe physics on null manifolds. This is a fact of life, and we can take profit of this in order to study flat holography. So if I start with Minkowski space, or asymptotically Minkowski space, and I do a conformal compactification to draw this Penrose diagram, I can consider the conformal boundary of this manifold that we call null infinity. There are two pieces, future and future and past null infinity. And this is going to be a Carolean manifold by virtue of what I said. And since we are doing a conformal compactification, it will inherit a conformal structure. So that's why I'm going to abundantly use the fact that null infinity, which is the holographic screen where we would like to define a holographic dual for gravity in flat space, is a Carolean conformal manifold. And I'm going to first, in this talk, define what is a Carolean conformal evolution equation, the analog of the conservation of the stress tensor, and apply it to a specific case in the gravitational bulk theory. Of course, don't hesitate to interrupt me if there are any questions. And so as a starter, I will do a reminder and also a slight generalization of the Lorentzian case, where we are going to see another object appearing in addition to the stress tensor. So if you consider a d plus one dimensional manifold, smooth manifold, d dimensions of space, one of time, you can, as usual, introduce a frame, which is equal to a coframe, a set of one forms that is written here, in order to describe your metric, which is just the symmetrized product, the square of the field line. Okay, and you contract indices thanks to this flat metric. Because we are in first order form, we have some extra symmetries, local symmetries that act on the field line. The first of which is a local Lorentz rotation with this matrix lambda, which is antisymmetric. And the second, because I'm considering conformal geometry, is going to be a local Weyl rescaling that I wrote here in infinitesimal form. So one way to think about this as a local symmetry is to remember that we are not going to look at one particular metric in our Lorentzian manifold, but at conformal class of metrics. And this transformation is given by this Weyl factor here. And as usual, we also have diffeomorphisms acting on the curved indices and not on the tangent indices. Okay, so armed with that, we can now introduce a connection for our manifold that I also write in first order form, which is a spin connection. And that is gauging the symmetries that I introduced before. So the antisymmetric part of omega is transforming as a connection for local Lorentz transformations. And the trace part of this omega is sensitive to Weyl rescalings. And I can introduce objects that are this capital D and curly D that are covariant derivatives with respect to both of these symmetries. From what you can see in this, the way that this spin connection transforms, there are two geometric quantities that you can extract from it that are covariant under both transformations. The first one is a non-metricity, and that is given by the symmetrized the symmetrization in the tangent indices of this spin connection and take away the trace. And I will always, in this talk, assume that it is 0. The second object is the torsion that is described by this two-form K. And we have a generalization of the Levi-Civita theorem saying that if you set both the non-metricity of the Weyl non-metricity to 0 and the torsion to 0, the connection is fixed uniquely. I highlight that there is a subtle point here because we are not in the usual Levi-Civita case. We also have Weyl transformations at play, and therefore there is a slight ambiguity of what we have to do with the Weyl connection, which is the trace. But if you assume that you have special conformal transformations in the game, you realize that this guy is pure gauge, so you don't have to worry about it. So I'm sure you're all familiar with this, but let me make a spoiler here. This is not going to be true in the non-Lorentzian world. So if you can build a connection that is Weyl metric compatible and torsion free, this is not enough to fix it entirely. It's going to have some free arbitrary data. All right, so now let me for a moment assume that I have 0 non-metricity and some torsion. And I'm going to assume that
I have some microscopic theory for some fields phi that I will assume that these fields are on shell. So I integrate out these microscopic degrees of freedom and I concentrate on how this theory couples to a background geometry with torsion. And this is called the metric affine variation. So here you can see the usual variation of the metric that is in this first order form written as delta theta A, and the response is going to be called the momenta. And we also have extra degrees of freedom contained in the connection, whose response I'm going to denote by omega AB, and following the standard literature, these are going to be hypermomenta or spin currents. Now, what can I do? I can evaluate this variational principle on shell, on local Lorentz and Weyl transformation, and obtain a bunch of constraints. If I didn't have any hypermomenta, this would just tell you that the stress tensor is symmetric and traceless, like we are used to. Here, however, I have hypermomenta, and now if you evaluate this variation on diffeomorphisms, you're going to obtain some generalization of the conservation equation involving the hypermomenta. These are geometric equations that take this form. R is the Riemann tensor. All right, so obviously I can set omega to 0 and go back to the known case, but as a fun fact, you can also consider a case where you have zero torsion and hypermomenta. These are still conservation equations with a shifted set of momenta, but the moment that you switch on the torsion and you have non-zero hypermomenta, these are never going to be conservation equations because part of the connection is independent. This has many, many applications. For instance, if you want to describe fermionic fields, we know that fermionic fields couple to torsion in the first order formulation. There are also some hyperfluid applications, teleparallel gravity. So this is all very well known and studied in the context of Lorentzian field theories. But now I'm going to do it for non-Lorentzian field theories. So first, are there any questions about this part? Okay, so let's start with an example that everybody knows, which is Galilean. So again, this non-relativistic, I prefer the term Galilean, which was studied, in fact, very long time ago by Landau and Lifshitz, which is describing Galilean fluid dynamics. So this is from the 60s, I believe, and this was revisited a few years later by Duval and Künzler using tools of Newton-Cartan geometry. So they are doing something very similar to Lorentz with torsion. They are introducing a frame, a connection. They realize that the connection cannot be completely fixed in terms of the frame, and they land in this type of equations where you have a right-hand side. So this is a non-conservation equation. Very good. So now let me finally define for you what is Carolian relativity. So it can be thought of sending the effective speed of light of your system to 0, and the symmetries that act on your manifold at this stage are the usual SOD rotations, translations in space and time, and a new type of transformation that is called the Carol boost, and which affects only time and not space. This is the dual to the Galilean boost, which affects only space and not time. One very important result that is going to be useful for us is that the conformal extension of this group of transformations, where you add scale transformation and special conformal transformations, is isomorphic to the Poincaré group in one more dimension. And you really have to think of this statement as the flat version of the fact that when you consider conformal transformations in d+1 dimensions, this is the same as the ADS isometries in d+2. So this is sort of step 0 of holography, this time applied to flat space. And from the point of view of ADS CFT, what many people are trying to make more precise is the statement that when you take a flat limit of ADS in the bulk, this corresponds to a Carolian limit on the boundary. Very good. So now let me also introduce a bit more definitions. What is a Carolian structure? This is the given of a degenerate metric G and a null vector n that is in its kernel. I call it n, it's null vector. In fact, it's such that when you contract this vector with the metric, you get 0 automatically. Again, because I'm interested in conformal geometry, a conformal class of Carolian structures is going to be given to this equivalence relation, where the weights here, -2 and +1, are synonymous of the fact that I have a metric and a vector. So now comes the important question. If I introduce a spin connection like before, what are the conditions such that can I build a spin connection that is both Weil structure compatible and torsion free? And the answer is a bit surprising. So first, you cannot always do that. Your geometry needs to satisfy some constraints, which is known as the vanishing of the geometric shear. So this is this quantity, the Lie derivative of the degenerate metric along the null vector. The trace-free part has to be 0. There is a point that is not terribly important for us here today, which is that the Weil connection is no longer something that you can completely gauge away, because the temporal part is fixed also in terms of the geometry. But the most important point is that parts of the connection are still free. If I take a spin connection, I ask it to be torsion free and compatible, parts of it are still unspecified. And so I can do the same thing that I did before. I can introduce this should be a frame, so not a coframe, where the first vector is my null vector n, and then I complete it with an orthonormal basis. Introduce a very compatible torsion-free connection, and you are naturally led to consider a variational principle with hypermomenta. And the equations that you obtain are not conservation laws, but evolution equations that takes exactly this form, which is just the same one as the relativistic with torsion. Okay, so if all of this is clear, I want to spend the last 5 to 10 minutes to tell you how we can apply these geometric observations to the program of flat holography, and in particular to gravitational evolution equations in the bulk, and how to re-encode them in terms of a boundary variational principle. So, okay, let's start with the basics, which is I will take Minkowski space-time and add some perturbations, some corrections to it in order 1/r. This is called BMS, Bandy, Vanderburg, Mester, and Sachs gauge, where the first 3 terms, they encode just empty Minkowski with a boundary metric gamma, and I can add some corrections in 1/r. So this is going to be my definition of an asymptotically Minkowski 4 space-time, where you can see already that this function, this tensor CAB here, so yes, maybe a bit of notation. So R is going to be a radial coordinate, parameterizing the distance to the boundary. So R goes to infinity is going to be the conformal boundary. U is a retarded time parameter that lives along the boundary, that is parameterizing each null geodesic. And XA, these are the 2 angles of the celestial sphere at infinity. Okay, so these are the objects that enter my expansion. This CAB, I choose it to be traceless in this gauge, is an arbitrary function that encodes gravitational radiation that reaches my null infinity. So you can take this metric and do a conformal compactification, realize that the boundary metric is Carolian. And this is because there is no term here that blows up as R squared, so the boundary metric has a 0 leg along du. Because I'm doing a conformal compactification, this is going to be actually a conformal class of Carolian metric. So we are already starting to see that we can apply the framework of the previous slides. As I said, this function CAB is something that is completely independent, and we can take its U derivative to define this useful new tensor that is encoding the flux of gravitational radiation at infinity. And there are 2 more objects that enter this expansion that is a priori infinite, which are the Bondi mass aspect and angular momentum aspect. And these quantities parameterize what type of space-time you are describing, if it has a sort of black hole or a rotation. All right, so these two quantities, they obey some evolution equations. And these equations take this form. They are a bit complicated. And the fact is that these are not conservation equations, because the charges that you can extract from a covariant phase space analysis of gravity are not conserved, because precisely of these terms, let's say quadratic in the news. However, if you study Einstein gravity in asymptotically locally ADS4, so with a negative cosmological constant, the equivalent equations to these ones are really conservation equations. These are known as the conservation of the holographic stress tensor, and this is one of the pillars of ADS-CFT. So the natural question that we are going to ask is, okay, these equations are not conservation equations, but at least can I recast them as Carolian conformal evolution equations, that's CRI, which is going to be the sort of similar statement for flat space holography. A few remarks to that end. The first is that CRI is indeed a Carolian conformal manifold with a specific connection. So Einstein's equation, so remember that for a connection on the Carolian manifold to be volumetric compatible and torsion free, I need to satisfy a set of conditions, which is the vanishing of the geometric shear. And this is guaranteed by Einstein's equation. So this is already starting to smell good. The second thing is that I always have an ambiguity in my connection. This ambiguity is sourced by the shear. So it looks like I'm going to consider a variational principle with hypermomentum. Does this hypermomentum have to be there? And the answer is yes. Because if you do, again, covariant phase space analysis of Einstein-Hilbert, there is going to be a term known as the Achtekar-Streubel potential that describes how much flux of radiation is going through null infinity. And this term takes the form variation of the shear times its time derivative. And we have to understand this as variation of the connections times its response, which is the hypermomentum. So now it's just a matter of writing down the dictionary. And here is the dictionary. So we are in small d equal to 2. The boundary metric can be written in this first order form. The clock form, which is the dual of the null vector, I choose it to be du in this case. And the ambiguity in the connection is parameterized by the shear. And now I have to specify what are my momenta and hypermomenta. So the hypermomenta, we find it to be given in terms of boundary geometry, namely some components of the boundary Riemann tensor, while the momenta contains this mass aspect m and angular momentum aspect ni, along with some geometric decorations. And if you do that, we showed that the Bondi evolution equations that I presented a few slides ago are nothing but Carolian conformal evolution equation understood from a purely boundary intrinsic point of view. So let me make an outlook. What we did was to understand general evolution equations on non-Lorentzian manifold, generalizing the work of Duval and Künzle to the Carolian case. This allowed us to clarify the status of these gravitational BMS evolution equations from the point of view of the boundary. And by doing that, we gain a geometric understanding of what is radiation and what are the charges. Now, of course, there are still a lot of open questions. The first one is how to obtain this dictionary from first principles, namely holographic renormalization, like what is done in ADS. Make a comparison with other works that involve a relaxation of the Bondi gauge in order to see if we match also in this way. And one very important thing that I haven't talked about at all is what could be the microscopic boundary theory that could reproduce this dictionary. And this is, of course, the next natural steps, and study the implications of these findings for scattering amplitudes in flat space and Carolian holography. And with this, I would like to thank you for your attention.
Thank you very much for the nice talk. So concerning the potential microscopic theory, what is the current status of the
So we need
concept of Carolian QFT or what?
Yes, so there are a lot of studies on Carolean QFTs or CFTs. These are mostly taken as the C goes to zero limit of Lorentzian CFTs, right? Okay, given the dictionary that I presented here, we see that we must find a theory that produces some hypermomenta. So it looks like, but I don't want to be too definitive about this, it looks like simple theories such as scalar fields, for instance, are not going to reproduce this. You need something that couples to the connection, so maybe a spinor, a fermionic field could be an option. But I have, yeah, for the moment we don't have a lot of progress to report on that.
Is there a Carolean version of the ON model that could connect to some flat space version of Hertzsprung gravity?
Right. Oh, thank you for asking. So no, because this is also another project that we are looking at. So, long story short, the flat space version of this ON model, for instance, these are very simple. They are going to reproduce a different sector, one that is non-radiating in flat space, right? Because if you start from a standard ADS CFT with Dirichlet boundary conditions, the equivalent of the shear, this term here, is absent because it sits in the source, right? And the Dirichlet boundary conditions tell you that you have to consider the depth. So we have to start from a different setup and different boundary conditions in ADS in order to do this. Thanks.
Any other questions?
So this flow equation, that this evolution equation that you wrote down, so these are essentially like word identities, like I mean on the dual theory. So and then what you mean that they kind of like, I mean, they are those of Carolean symmetry, I guess. I mean, mean that they generate as first that constraints the local symmetry, right? So essentially that's what you showed, right?
Yes. Yes.
Yes, actually the word identities associated with this equation will produce the soft theorems. If you do carefully the thing, so they really encode the BMS invariance, the BMS word identities of your putative dual theorem.
Okay. Thank you very much again.
Thank you.
Okay, so the final talk of today will be from Panagiotis Haralambous, who is going to tell us about mirrors at the edge of space-time.
Yes, okay. Hi everyone. Last talk of the day, the first day of the workshop. It's actually the first time I'm participating in this workshop, this annual workshop, and I'm really enjoying it so far. We've seen a lot of beautiful talks, and I'm grateful for being part of this list of speakers. Okay, so I'm here to talk to you about some ideas, mostly ideas, including some nice results that, well, as the title suggests, are built around the correspondence between two non-Harper surfaces that are consistently emerge when studying physics in curved spacetimes, and their causal structure. Yeah, these are the null surfaces of an horizon, and non-infinity of an asymptotically flat spacetime. I will be more explicit on how these are constructed. So I will, yeah, this talk is based on these two works. One is we released in June, and the other, well, we hope to be released either tomorrow or the day after tomorrow. So if you are interested, I can send you this once it's released. But okay, let me start with some definitions. How do I do this? Okay. Good. So realize, okay. I like to present things with pictures, especially when I want to show some definitions of results without being too formal. And I realize that Penrose diagrams can be intimidating for some people who never saw them before. So let me start with a very brief description of what these are. Penrose diagrams are essentially a way of compactifying entire space-time onto a finite dimensional surface, for example, on a drawing on a piece of paper, which have the characteristic property that they preserve the causal structure. In other words, that light rays propagate at 45 degrees straight lines. For example, this is what the Penrose diagram of the four-dimensional Minkowski space-time looks like. It is a half diamond, which is bounded by these 5 types of conformal infinities. This I plus and I minus are the time-like infinities. This I0 is called spatial infinity, and this scri plus and scri minus and the null infinities. Physically, these can be understood in the following way. Spatial infinities were all space-like slices, and future and past time-like infinities where all massive bodies come from an end. And last, more importantly for this talk, we have null infinities located at these tilted sides of the diamond, which indicating that these are null happy surfaces. Future null infinity is the place where all radially outgoing radiation ends up, and past null infinity is where ingoing radiation comes from. Okay. Now with this definition, I can answer a very basic question that defines the first part of the correspondence. This is the set of an asymptotically flat space-time, specifically a space-time that is asymptotically flat near null infinity. Now, okay, answering this question was a necessary ingredient for actually theoretically predict gravitational waves, and it was quite hard to formulate this definition. This was only achieved in the 60s, almost 50 years after Einstein gave us general relativity. And by these seminal works by Bondi, Vandenberg, and Metzner, and Sachs, which followed a more coordinate-oriented approach to define asymptotic flatness near null infinity. What they essentially did is they chose a nice gauge, which was adapted to physical quantities. Namely, they chose null Gaussian coordinates adapted to outgoing null geodesics. This V is a retarded time here. R is some radial leg coordinate, and XA are the spherical angular coordinates that one would use in Minkowski spacetime. Okay, so the first line in this line element is precisely reflects asymptotic flatness, which loosely means that the spacetime looks like flat at large distances. And the first line is precisely the line element for Minkowski spacetime. And the second line describes how this Minkowski at infinite distances is glued together to the bulk. One observes this characteristic field, this CAB field, which as Simon presented us in the previous section, was realized to describe gravitational radiation. Okay, I will ignore this. Okay. Right, but the key element here is that the asymptotically flat spacetime can be visualized in this way using Penrose diagrams. It's something that looks like that at large distances. Okay, now on the other side of the correspondence is a horizon located at finite distance. Now this slide is a bit heavy with some formal definitions, but the point of this slide is that one can analogously follow a coordinate-oriented approach and parameterize the geometry near a generic horizon, not even an event horizon, a very generic horizon, by using this gauge that is adapted on now ingoing null geodesics. In particular, V here is an advanced time coordinate, rho is a horizon center radial like coordinate, and similar to before, XA are some angular like coordinates. To analyze the geometry near a horizon, what one typically does is one introduces two null vectors. One is this L vector, which becomes a null normal on the horizon. And the other is this N vector, which is aligned with ingoing null geodesics on the horizon. This then allows to construct identifying the intrinsic metric, this Q field here, which is realized to be degenerate on the horizon, reflecting the fact that the horizon is n null happy surfaces, while the existing geometry is captured by this set of quantities that have some special names, which I don't want to get into. Let me just briefly explain what they physically mean. This capital theta is the expansion of the null norm on the horizon. It describes how the horizon area changes in time. The sigma b is called the shear, the longitudinal shear. It is the shear associated with this null normal on the horizon. And this omega A is a twist or a Haji-Sek-1 form, which captures frame tracking effects associated with the rotating horizons. This cut pattern here would be surface gravity of an even horizon. I don't want to get more than that. So let me now go straight to the next slide, and I'll present this correspondence that I mentioned in the beginning. There is nice observation that I think is not emphasized enough in the literature, that all asymptotically flat spacetimes can be understood to be conformally isomorphic to the geometry near a horizon. And you can really state as conformal isomorphism. This conformal isomorphism comes in the form of these discrete spatial inversions, where R here is this near null infinity radial coordinate, and rho is this near horizon radial coordinate. If you do this spatial inversion, you precisely get that the asymptotically flat spacetime is conformally the same as the geometry near horizon, but not near a generic horizon. This dual horizon has some specific properties, which are summarized in this dictionary. Namely, the exact statement is that all asymptotically flat spacetimes are conformally isomorphic to the geometry near a horizon that is non-expanding. Its expansion and longitudinal shear are zero. And furthermore, this dual horizon must be non-twisting. The Haji-Sek-1 form must vanish, and also non-extremal. So it's quite a restrictive dictionary, but I will hint that there are some generalizations. Yes, Adrian?
Yes, I have a question, because how this result depends on the gauge you choose.
Right.
Because actually at square plus, you can allow for an expansion if you don't choose the body frame.
Okay,
condition. So then, if you perform your coordinate transformation, you will find an expanding horizon, but still without shear, intrinsic shear.
Can find expanding horizon? Okay.
Because the longitudinal shear has to vanish by virtue of Einstein's equation at infinity.
Right.
So I don't see how you will recover this shear at the horizon. But the expansion, I think you could recover it.
Right, indeed.
If you relax a bit the gauge at an infinity.
Indeed, I think you cannot actually recover the shear on the horizon. I think what you say is true, but I will hint that it could be possible to do this, but in a very non-local way. I don't have an explicit result. I just have hints that it could be possible.
What do you mean by non-local? Mean that
in the way that it's actually phase-space dependent. It's not something that acts locally in coordinate space. It's something that would act locally in phase space, not in coordinate space. But what I'm saying is really a case, not an exact. Okay, maybe we can.
To understand your statement, so this is a theorem that you are the next slide, the slide where you have something which is boxed. So this is what you are demonstrating.
Yes.
Okay.
Yes.
Yeah, but this is dependent on the gauge choice at infinity.
Right. It's really this statement that you can identify these inversions which show that these two asymptotic views of these two the geometry near these two asymptotic surfaces somehow admit the same expansion in these different inverted coordinates.
And your alpha is constant, or is
alpha here is some constant length scale, some arbitrary length scale.
Okay.
You can think that you can relax it to be some function, for example, of the angles, but it doesn't change the fact that the horizon must be non-twisting. This dual horizon must be non-twisting.
Yes, but now if you make it time dependent or u dependent.
If you make it u dependent, okay.
Then maybe you should get expansion of the horizon.
Right.
But you
well, you get expansion but not shear. Yes. You get something.
No, the shear is just.
Right. You get expansion but not shear. Right. No, you're right.
Thank you.
Okay. Yeah.
So you said like the horizon should be extremal or non-extremal, like
here it will be extremal for this
Extremal,
correspondence, right?
So this is basically these two kind of like a
Yeah, I mean, you can think that this is like a fancy way of saying that the ADS is conformally flat. Yeah, essentially. Right. Okay, good. Right, but that is crucial remark here that this dictionary is not very physical because it's a correspondence and not a symmetry, right? It tells you that there is correspondence between two different type of geometries, but these geometries don't have to live in the same space-time, and in fact, they almost never do. Okay? The prototypical counter example to this situation is the extremal raster-Nostrum black hole in 4 space-time dimensions. Here, the geometry of this extremal raster-Nostrum black hole is an electrovacuum solution whose horizon is extrema. Okay, it's a perfect square. This is a discriminant function, and as was discovered really by Couch and Torrens in the 80s, this geometry has conformal isometry, which is precisely in this form of discrete spatial inversions. This is known as a Couch-Torrens inversion. It precisely do what this correspondence sense does. It exchanges the horizon with null infinity, but now the horizon and null infinity that are exchanged are actually part of the same space-time. So you see that this Penrose diagram is connected, is not disconnected like the previous statement of the correspondence. Right. And now that we have this example of a self-inverted space-time, for which these inversions are actual symmetries, conformal symmetries, we can make a statement about physical implication. We can actually extract physical constraints. So here is how this can be done. Using this example where I'm studying a probe scalar field, which is in a curved background, in the background of a extremal raster-Nostrum black hole. The equation of motion is this Maxwell-Klein-Gorton equation, which when analyzed near adapting coordinates that are appropriate for studying physics near the null surface of interest, can be broken down to these two problems, equivalent problems. Near non-infinity, it satisfies this equation with this particular operator, which is to be understood to be solved by this this expansion of the scalar field into near non-infinity modes. Yes, 1 over r to some power modes. The second line is the same equation, but now adapted in a coordinate system that is suitable for analyzing equations of motion near the event horizon, where now the scalar field is expanded to near horizon modes, rho to some power modes. Right. So what I will show is that the Couch-Torrens inversions actually imply a matching of data between near non-infinity modes and near horizon modes, a direct consequence of which will be the identification of two sets of conservation laws. So let me start with what happens near null infinity. Near null infinity, one gets this set of Newman-Penrose constants, which are really some projections of this combination of these near null infinity modes. And these combinations have the mysterious property of being exactly conserved, at least at the linear level. Let me say here that these Newman-Penrose constants, as far as I know, we don't really know why they exist. I mean, they are not associated with any symmetries. They are somehow some free conservation laws that nature has provided with us. And there's an analogous story that happens on the event horizon, at least for the extremal black holes, where one instead has some particular combination of these near horizon modes called the Aretakis constants. These again have some different physical meanings, but there are still some infinitely many conservation laws that we get for free, and we still don't really know why they exist, but they are here, they are there, and they are part of the data of the problem. Okay, now I don't want to get too technical, so let me go directly to the punchline, that after doing some pretty standard manipulations using the fact that the Couch-Torrens inversions are conformal isometries of the background, one reaches the conclusion that there exists this matching condition between near null infinity data and near horizon data. Okay, and a direct consequence of this matching condition is precisely that the Newman-Penrose constants and the Takis constants will be exactly the same. And now there is a relation between two very different objects. One is defined at null infinity, and the other in the horizon. With this, let's see, good. Just for completeness, let me just mention that we were able to generalize this procedure to all types of spin-weighted probe fields. This psi S here captures some probe fields labeled by this spin-weight S. When S is equal to +1, this describes electromagnetic probe fields, and when S is equal to +2, describes gravitational probe fields in the background of the Weierstrass-Nostrom, extremal Weierstrass-Nostrom black hole. Again, the existence of Cauchy-Lorentz inversions implies these matching conditions. A direct consequence of which is the exact equality between these near null infinity constants, the Newman-Penrose constants, and the near horizon Takis constants. Okay.
So these constants, like they are Takis and Stoker, they exist also for other type of perturbations, not just for fingers?
Yes.
Okay.
Yes. Also, they are for electromagnetic and gravitational perturbations. Yes. Right. Okay. Now let me start generalizing stuff, because the correspondence I mentioned was pretty limited, right? It involved null infinity, a paraspecific flat spacetime, and a horizon that had two very specific properties. The horizon was extremal and non-rotating. Now we'll give some hints that this is probably generalizable without these constraints, although I don't have an explicit answer of how this happens. And starting with the case of a black hole that is rotating but still has a Cauchy-Lorentz inversion symmetry. So here's the geometry of the extremal Kerr-Newman black hole. This is thing here, which is really the rotating version of the extremal Weierstrass-Nostrom black hole. Looking at the equations capturing probe fields, the field equations capturing probe fields in this background, what one realizes is that one still finds that there exists inversions, Cauchy-Lorentz inversions that are exact conformal symmetries of the equations of motion. But now the difference compared to the Weierstrass-Nostrom's paradigm is that these inversions are now phase-space dependent, right? So they have this weird, I would say non-local coordinate space form, which becomes linear only when we use this mode decomposition of the probe fields, where M here is a azimuthal number, and omega is the frequency of the probe field. So there's still, the Cauchy-Lorentz inversion is still there. We don't see it if we just focus on the coordinate space, we just focus on the metric. But it's still there and acts on probe fields in the background of this geometry. Okay, good. And we follow procedures similar to what we did with the Weierstrass-Nostrom situation. One again realized that the corresponding Newman-Penrose constants and their Takis constants associated with axis symmetric perturbations must be exactly equal. Right, so this is the first hint that shows that the requirement of a non-twisting horizon might be relaxable. Okay, and the other condition that was pretty limiting was that the horizon must be extremal. And now I will argue that this might not have to be the case, with the characteristic example being this beautiful geometry called the Lugol geometry. It has this form, it's still an electrovacuum solution of the Einstein-Maxwell theory, but now in a space-time that is not asymptotically flat. So there's this extra piece here. K is equal to 0 for asymptotically flat space-time. This is the extremal Weierstrass-Nostrom paradigm. K is equal to -1 for asymptotically added de Sitter geometries, and equal to +1 for asymptotically de Sitter geometries. And for this last case of the asymptotically de Sitter geometry, this actually describes a non-extremal black hole whose Penrose diagrams is this monster here, but it's somehow it's very beautiful. It's very symmetric. And this class of geometries are all with a Cauchy Lorentz inversion, regardless of whether it's flat and the asymptotically de Sitter or asymptotically de Sitter. For the de Sitter situation, it acts on precisely a non-extremal black hole, and that's what one will expect it to do. It exchanges the event horizon, the non-extremal event horizon, with the cosmological horizon, these blue lines here on the Penrose diagram, yes. And also exchanges the inner horizon with another with another horizon located at some negative radii. So yeah, these dotted lines here on this Penrose diagram. And another thing it does that appears to be a generic property is that it preserves some particular surface. Here is this R equal to M surface, which eventually can be understood to be the location of an unstable photosphere. So somehow there are these properties of this Cauchy Lorentz inversion. They tend to exchange null hyper surfaces and preserve some unstable photon shell, photosphere. Okay, I'm not going to be too explicit on what this does. Thank you. Yes?
I'm a bit confused because you are in the case of asymptotically de Sitter.
Yes.
But this Penrose diagram looks a lot like Minkowski.
This one?
The Penrose diagram looks a lot like Minkowski.
Well, typically this dotted pad is missing. It corresponds to some negative radii. Well, yeah, this is the Penrose diagram for.
So should I think of this as embedded in some patch of the Sitter?
No, not really. You can imagine this is it. Well, this is extended. We want to only have the minimum part of the between the node diagram. No, this will do.
Well, these are things, right? I would have said it to be rotated by 90 degrees.
Yeah. Okay, good. So I guess this is the part that is typically shown, right? Where the aperture of the box is going to be here, I guess. So it's here, right?
Also, you're considering R which can be positive and negative. So
yes.
You also have
yes, well, as far as I know, this is the standard way to present black hole geometry in the system. Okay. Right, so my point here is that we have an explicit example where the Cauchy Lorentz exists for non-extremal black holes. So the extremal clustering might be too restrictive. In fact, this is something we are studying in this book that should appear in some coming days, where we construct an explicit inversion that acts on the non-extremal Kerr black hole, but only on a particular subsector of its properties. But I don't want to get into it right now. Let me just go ahead and finish this talk. So in summary, I argue that there is this correspondence that between a generic asymptotically flat spacetime and a horizon and the geometry near a horizon that is non-expanding, extremal, and not twisting, with explicit with a self-inverted example being the extremal Raster-Nostrom black hole. This self-inverted property provided with some matching conditions at the level of the data, a direct consequence of which was this identification between the near null infinity Penrose constants and the near horizon Aretakis constants. And in the last slides, I also showed possible extensions that might hold, that might say that its correspondence is more generic. It doesn't just apply for extremal and non-twisting horizons. In fact, we expect it to apply for also non-extremal and twisting horizons. So here is a list of possible future directions. Whereas everyone is tired, so I'm going to stop here. Thank you, everyone. Enjoy the rest of the conference.
So yes, Paolo, thank you for the talk. An important aspect in all this business are symmetries, right?
Yes.
So do you have some comment about the presence of PMS, Poincaré, larger, lower dimensional, I don't know, symmetries at the horizon?
Right, okay, I guess this is somewhere you can answer the question in many ways. It's true, but since both are not surfaces, both are equipped with Caronian structure, they share the same symmetries. I guess at non-infinity, what might start restricting stuff?
Not conform.
Hmm. Also on the horizon, because it's a Carolean surface.
No, but yes, so it's not BMS, but under restrictive boundary condition, you can make BMS atomic.
Right.
There's no conformal structure on the horizon. There's a conformal structure on the horizon.
No, there is not.
So from that, it's already very different.
No, but I think when you kill the extension, you can still atomic BMS. I have to read again this paper by Flanagan and Coulter.
Yeah, there are a lot of if that, and if not that, you can start and make the group bigger or smaller.
Yes.
Yeah.
But in any case, you have BMS acting on scribe and even LW up to infinity. Then you can basically reverse engineer all the limit towards infinity and see if it still acts on the horizon. Yes, and that was the spirit of my question. Yeah. Also, I know that Roman Selim has a paper on this.
Right, yeah, it's right.
Here,
Yeah,
but since you quote also a paper.
Yeah, they include their later one.
Yes, exactly. So I just wanted to know what are your views on that?
On that?
Can you make some comments about the symmetry? So.
Right, okay. I mean, they still try to motivate the existence of these. Good. So Adrian is referring to this paper by Roman and Zwickel, which...
Yes, but also to yours, because
okay, but we did a study like the horizon here, yes. Maybe that's something in preparation, which, okay, this should be 26, it's not really. I don't think will appear.
Sorry.
Yeah, sorry. Yeah, sorry about that, right. It's something we'll be working on, but we realize that it's more subtle than we thought. Yeah, so Adrian is referring to this W1 has infinity symmetry, celestial symmetries that one encounters at the celestial or Carolean communities are frequently encountered. And these were initially realized near null infinity, and the question is whether these can also be realized on the horizon, on the finite distance horizons. And this paper by Roman and Céline suggested that this is still possible, motivating the existence of these W1 plus infinity symmetries precisely because of these special inversions, the fact that you can map an infinity to a horizon. Right, I mean, they made this motivation. Now, anything after that, I'm also a bit blurred with the details. We're trying to get in touch with them to clarify some of the details. So I don't want to say something wrong that it might be proved.
That's what, long story short, it's work in progress.
It's work in progress,
okay,
yes.
Then sorry for the question.
Okay. It's work in progress, yes. Yes?
So, I think I probably asked you this before, but I don't remember what you
yes.
So it is like, I mean, horizon kind of like asymptotic region duality related to, so first of all, it's a four-dimensional thing only, right?
Oh no, actually this is very generic, right? Doesn't care about the space and dimensionality. The interpretation of the fields, yeah, space-time is
Because
dependent.
you mentioned like, I mean, the string care, correct? I mean, like, I mean,
right, yes, sorry, yeah, these examples, yes, these are for only 4 dimensions, yes.
Right.
Yes.
So in this case, like, I mean, do you think this is related to the electromagnetic duality of the bulk pi tensor?
Yeah, I remember that question. I still don't have a good answer about that, yes. Yeah, well, I remember. But there are strong hints that could be possible because of this. In higher dimensions, the inversions are still there, but they don't act on black holes, they act on self-dual p-branes.
Right.
Yes, so
What do we call this duality?
What do we call this? What we call the couch stories.
Basically, the question is there a self-dual point? In some sense.
A self-dual point of these inversions? Okay, yeah, this is something that we're trying to understand, and we think that the self-dual point in the geometry itself are the bottom spheres. Although this answers, we're talking about the class of geometry.
The relation more precise, but if you make it, if you call it something duality, then there is a self-dual point where you have some enhanced symmetry, things like that. And since I saw W1 plus infinity, my mind went probably that relates to...
For this twist or self-dual, right, we don't know.
Saying work in progress ends all discussion.
Okay.
but I think the fixed point for this injection is just flat space. Yes. Yes. Exactly.
In real chord. That's my guess.
Yes, exactly. Just flat space is enough coordinated. Because you need a wedge so somewhere. If you just have two null hyper surface, just this or this, and if you want to identify them, the flat space is the void.
Yeah, well,
Yeah.
I don't see anything else, so thanks to Panos and all the
Second half,